This is my second video on nonlinear dynamics. Please check my earlier video on fixed point in one dimension given in the description below. Here we study about the fixed points in two dimensions. We study about the nature of the fixed points based on the dynamics of the perturbations around the fixed point. So this is that's all in this video. This is our aim. So let's start. Let's take the dynamical equations in two dimension. It means we have the 2 degrees of freedom. We denoted it by x1 and x2, and this is the equation 7 is the dynamical equation. So let's take the fixed point denoted by x1 bar comma x2 bar. So this fixed point satisfies the equation 8, where the right hand side of the equation 7 turns out to be 0. So what does it mean? It means that if you start to evolve the system at this fixed point, it remains in the fixed point throughout all the time. So to analyze this nature of the fixed point, we consider the perturbation around the fixed point, and we see how the perturbation grows around this fixed point and study the nature of the fixed point. So let's take the equation 9 and 10, which tells you about the perturbation around the fixed points, or the around the 2 degrees of freedom. We denoted it by delta x1 and delta x2. So we substitute this equation 9 and 10 in the dynamical equation 7, and we find out how delta x1 and delta x2 grows with time. So once we substitute, we'll get then equation for delta x1 and delta x2, that's given in equation 11 and 12, and we just have written higher order terms that considers the higher powers of delta x1 and delta x2. So now we can write, by neglecting the higher order terms, we can write this equation in a matrix form. That is given in equation 13. This the matrix M given in equation 13, we call it as a Jacobian matrix. So to calculate the Jacobian matrix, we have to differentiate the function with respect to 2 degrees of freedom and find out at the fixed points what are the values for this matrix. So now substitute for delta, differentiate the equation 11 with respect to time again. We'll get the second order differential equation for delta x1, eliminate the delta x2 part by using the equation 12 and substitute back in the equation where we have differentiated. We get a second order differential equation for delta x1. So we can solve this equation 14, and the solution will be of the form as given in equation 15 and 16. So these are the solutions for the delta x1 and delta x2. These are the perturbations, how it grows with time, and it depends on the lambda 1 and lambda 2. So, and also ABCD, these ABCDs are constant, depends on the initial conditions. These lambda 1 and lambda 2s are the eigenvalues of the matrix M. This M is the matrix which we defined in equation 13 earlier here. This is the Jacobian matrix. The eigenvalues of this Jacobian matrix decides how the perturbation grows with time. So now we will choose different cases for these lambda 1 and lambda 2 and see how the perturbation grows with time. So now let's take the case 1, where we have the lambda 1 lambda 2 are real less than 0, and we are taking lambda 1 equal to lambda 2. So what happens in this case? In this case, we can see from the perturbation solution, the lambda 1 when it is negative, lambda 2 when it negative, with time it decays with time and goes to 0, and same for the case of delta x2. So this one and both the terms decays to 0. And the another interesting part is, if you find the slope in the x1 x2 in the dynamical degrees of freedom plane, dx by dt turns out to be constant. What does it means? That the perturbation does not grow with time, and also in the two eigen direction it grows with the same slope. So it forms a with this these kind of stable point, we call it as a stable star, because the slopes in the x1 and x2 plane is the constant, so it decays with time in the same speed in all directions. So this kind of fixed point, we call it as stable star. Now if we choose lambda 1 lambda 2 as greater than 0 and lambda 1 equal to lambda 2, it means that in the perturbation solution we can see that with values lambda 1 and lambda 2 greater than 0, it grows with time. So therefore it does not decays to 0, so it continuously evolves. It means that after perturbation the system does not comes back to the system does not comes back come back to the fixed point. So we have even though we have dx d by t as a constant value, it moves away from the fixed point with time. And the next case is lambda 1 is less than lambda 2, but both of them are real and less than 0. In this case, we both of them decays to 0, delta x1 and delta x2 both decays to 0, but it is not a constant value, so it gives a parabolic trajectory around the fixed point. You give a perturbation around a fixed point, it grows back, it comes back to the fixed point with a different speed. So this kind of nature we call it as this kind of fixed point we call it as a stable node. So if we take greater than 0, lambda 1 is greater than lambda 2 and both of them are greater than 0, then this perturbation grows with time, it does not come back to the fixed point, and we don't have a constant, the slope is not constant in the x1 x2 plane. So we'll get unstable node both. If you give small perturbation around the fixed point, it grows with time and it moves away from the fixed point. This kind of fixed point we call it as unstable node. The fifth case is lambda 1 is less than 0, but lambda 2 is not less than, it is greater than 0. In this case, one decays with time, other will grow with time. One decays with time and the other will in both the delta x1 and delta x2. So it forms a in one direction it comes towards the fixed point, in the other direction it moves away from the fixed point, so it forms a saddle point. So it is an unstable fixed point, and we call this kind of fixed point as a saddle point. So the sixth case is both eigenvalues are complex number, but they are complex conjugate to each other. In this case, it depends on the perturbation, how it grows. It mainly depends on the alpha values. So these cause for the beta gives the rotational part, and alpha tells us how the nature this the perturbation grows with time. So perturbation changes with time. So if alpha is less than 0, then if you give a perturbation around the fixed point, it moves towards the fixed point with time. It decays with time, it goes to 0, so it comes back to the fixed point. So this kind of fixed point we call it as a stable spiral. If alpha is greater than 0, then if you give a perturbation around the fixed point, it moves away from the fixed point because alpha is greater than 0 and the perturbation grows with time. And the last case is when alpha is equal to 0, it does not move away or will come closer to the fixed point. If small perturbation on the fixed, it just evolves around the fixed point. We call it as a center for this case. Thank you. In the next video, we'll study about van der Pol oscillator.